Good day, my name is Joe Valliarampath and I'll present to you my doctorate research titled Improving Linearity Utilizing Adaptive Predistortion for Power Amplifiers at Millimeter Wave Frequencies. This research work was supervised by Professor Saurabh Sinha. The agenda for this presentation is as follows. I shall explain the problems associated with power amplifiers at millimeter wave frequencies, in particular focusing on the aspect of power amplifier linearity. Also, I shall provide a background into linearisation and the need for it, describing how it fits into my research. The hypothesis and research questions will be presented to show how this research was evaluated. The current linearisation techniques implemented at 60 GHz, as well as the technology node that was used, will also be described. I shall then go through my design, results, and chip layout. At the end, conclusions will be presented, making reference to the hypothesis and research questions. Possible future work will also be mentioned. During this presentation, I'll be at times using PA to represent the short form of the power amplifier. The wireless transmitter, as shown in this figure, comprises many subsystems, but of particular interest is the power amplifier. The power amplifier is needed to amplify the transmitted signal so that it can be detected at the receiver. Unlike wide line communications, wireless systems must share a common transmission medium. The available spectrum is therefore limited. The demand for greater spectral efficiency has resulted in orthogonal frequency division multiplexing, or OFDM, being considered as the modulation scheme within the millimeter wave frequency band. OFDM is sensitive to disturbances such as nonlinear amplification, which causes distortion of the output signal. These distortion components are a serious problem as they can be mistaken for the desired signal. The odd order intermodulation or IM distortion products, especially the third order harmonics as shown in this figure, are of greatest concern. These third order IM products lie very close to the desired signal and results in spectral regrowth and cannot easily be rejected by filters. It is therefore important that the power amplifier operates linearly to avoid these distortion components. In order for the power amplifier to operate linearly, some sort of external linearisation technique is needed. There are a number of linearisation techniques available. These include the feedback technique. This uses the input and output power amplifier signals to compensate the distortion components. However, sufficient loop gain is generally required. Feed-forward subtracts the input and output of the power amplifier signals. The major disadvantage of this method is the complexity of the system. Link and EER are two similar techniques. The major drawback in both of these techniques is managing the synchronization between the amplitude and phase signals. And then we have the predistortion linearisation technique. This technique works by using the inverse characteristic function of the power amplifier in order to linearise the power amplifier. An ideal predistortion circuit will give you a flat gain and phase as shown in this figure. The use of the predistortion circuit has the following advantages. It provides wideband linearisation, it is stable and simple to design and implement. This figure shows the output power of a power amplifier without predistortion linearisation, shown using a solid line, and the improved ideal response shown in the patterned line after predistortion was applied. Higher operating points can be obtained using predistortion, therefore resulting in larger linear output power. Predistortion linearisation can be split up into digital and analog predistortion. Digital predistortion is mostly found in the baseband region and uses algorithms within lookup tables to realize the predistortion function as shown in the top figure. The analog predistortion method uses a nonlinear device such as a diode. However, it can also be made adaptable as shown in the bottom figure. This slide highlights my research focus and hypothesis, which states, if the linearity of power amplifiers is related to the distortion in power amplifiers, then if analog adaptive predistortion or APD is used to reduce the distortion in power amplifiers, this will improve the linearity in power amplifiers. Based on the hypothesis, the following secondary research questions can be asked. Firstly, how to realize the APD and integrate it with power amplifiers at millimeter wave frequencies. How much linearity improvement can be achieved with the implemented APD? Lastly, how is the overall performance of the amplifier influenced with the use of the APD? This slide shows the current linearization techniques at 60 GHz. All these techniques are based on CMOS technology, and the linearity improvement is shown in this table. Research work shown in 3 uses an adaptive digital baseband predistortion technique. 4 uses a cold MOSFET as the linearizer in the analog predistortion technique. 5 uses a self-healing algorithm to improve the linearity of the power amplifier. To the author's knowledge, no adaptive RF predistortion linearization techniques have been used at 60 GHz. The requirements to integrate analog and digital circuits and extend the capabilities of the same power amplifier chip have become very important. Owing to higher gains and current densities required at microwave and millimeter wave frequencies, bipolar devices have been the preferred choice at higher frequencies. Previously, gallium arsenide based technology was the preferred choice. However, with recent advancements in silicon germanium HBT technology, especially in terms of reduced manufacturing costs and power consumption, have made this technology favorable at these frequencies. Silicon germanium HBTs are formed with the grading of germanium across the silicon base as shown in this figure. This reduces the band gap in the base region, resulting in the base transit time reducing. The net effect is that there is an increase in the transition frequency and current gain. The IBM BiCMOS technology consists of both silicon germanium HBT and MOSFET active devices. The silicon germanium HBT used in the design has a transition frequency greater than 200 GHz and is well suited for power amplifier applications at 60 GHz. The major design constraint with the silicon germanium HBTs is the low breakdown voltage, which reduces the available output power. The CMOS transistors can be used in the digital circuitry. The Process Design Kit, or PDK, comes with a full library of passive devices. These include resistors, capacitors, and spiral inductors. The PDK also allows additional passive devices to be constructed, such as transformers, which can be used as a power combiner to increase the output power of the power amplifier. At millimeter wave frequencies, system performance is affected by the device layout. The layout of the circuit will also introduce parasitics, especially in the interconnects. The PDK includes the parasitics and process tolerance for each device. The design guideline also provides a detailed analysis of each device's performance, including the parasitic values under various simulated and measured conditions for comparative purposes. The designer can therefore measure the parasitic effects for different conditions. In order to design the predistortion linearisation technique, a mathematical understanding of the nonlinear components and how they relate to the IM distortion components should be obtained. The dominant IV and CV nonlinearities found in the silicon-germanium HBT result in the following nonlinearity components. The collector current IC is a nonlinear function of the control voltage V pi and relates to a nonlinear transconductance. The base current IB is also a nonlinear function of the control voltage and therefore follows the nonlinear characteristics of the transconductance. The diffusion capacitance C_diff is directly proportional to IC and is therefore inherently nonlinear. The input signal in this figure is presumed to be small and therefore the nonlinear components are described as weakly nonlinear. To understand the behavior of these nonlinear components, Volterra series analysis is performed on the common emitter HBT model shown. The Volterra series is a powerful tool used for modeling and calculating the distortion components of weakly nonlinear systems with memory effects. Other simpler nonlinear models such as the Wiener, Hammerstein, and memory polynomial nonlinear models are also available. However, these models are variations of the Volterra series model and have limitations because of their simplified approach in characterizing the system. Using the Volterra series analysis, the first order Volterra kernel at node 2 is shown in equation 1. The second order nonlinear components of the silicon-germanium HBT are shown in this figure. The second order Volterra kernels are obtained by placing the second order nonlinear currents and capacitors in parallel to the linear current sources and capacitors. The input voltage is now shortened. The second order Volterra kernels are then obtained using Kramer's rule and Kirchhoff's current law and are shown in equations 4 and 5. Similar to the nonlinear secondary components, the third order nonlinear components are placed in parallel to their linear components as shown in this figure. The third order Volterra kernel is shown in equation 6. The third order intermodulation distortion ratio is given by equations 8 and 9. From equation 9, it can be seen that increasing the bias current and the gain will reduce the third order intermodulation distortion component and improve linearity. The point at which the third order intermodulation distortion component equals the fundamental component is known as the input third order intercept point. The higher the input third order intercept point, the more linear the system is. The input third order intercept point for increasing bias current is shown in this figure. A transistor size of 0.12 micrometer by 16 micrometer was used to simulate the input third order intercept point. As shown in this figure, the linearity increases sharply for small bias currents and is then followed by a gradual increase in the linearity as the bias current increases. The input third order intercept point begins to taper off for bias currents greater than 23 milliampere. In terms of the large signal analysis, all power amplifiers suffer from the nonlinear effect of saturation, where the gain begins to decrease with increasing input power, known as gain compression, as shown in this figure. One cause of this phenomenon is due to device heating caused from the power dissipation of transistors, resulting in self-heating. This is most noticeable at high current densities. However, the main cause of gain compression is the overdriving of the RF signal away from the device's linear region of operation and into the device's ohmic region. The result of this is that the output RF signal is now clipped. Therefore, the gain compression is directly linked to the Q bias point of the transistor. By providing an increasing gain at certain measured output power levels will ensure a constant overall gain such that the output power remains linear until the saturation limit has been reached, at which point no further linearity improvement can be achieved. The figure in this slide shows the power amplifier schematic. The power amplifier is a three-stage class AB power amplifier that uses a temperature compensation bias network. The chosen bias network provides three important functions, namely biasing the power transistors at the correct bias point, extending the breakdown voltage limit, and providing temperature compensation. The matching networks were done using load pull simulations. This power amplifier was designed for maximum output power. The three-stage power amplifier is unconditionally stable for the design bias points. The APD design is shown in this figure. The parasitic values for each device were included in the optimized design values. It uses a variable gain amplifier or VGA, a power detector, an analog to digital converter, control logic, and a digital to analog converter or DAC. The feedback path from the output of the power amplifier to the detector and back to the input of the power amplifier makes the predistortion system adaptable. The VGA is actually the first stage of the power amplifier that is driven by a control voltage supplied by the DAC. The APD implementation and the power amplifier response are shown in this slide. A corresponding digital signal is generated as shown by the output of the control logic circuit when the detected output power of the power amplifier satisfies the conditions tabulated here. This digital signal then commands the DAC to output the desired control voltage, which then drives the VGA. Using the control logic as described in the table, the results for the gain and output power of the linear power amplifier are shown in this figure. Increased gain and linear output power of the power amplifier are achieved when APD is applied to the power amplifier. The gain of the linear power amplifier is fixed around 18 dB, resulting in an increased input power 1 dB compression point of -6 dBm and improved linear output power. The linear power amplifier shows an improvement of 2.5 dBm, at which point no further linearization can be applied and the linear power amplifier begins to saturate. These figures show the S parameters under different bias conditions. The notch of the S11 parameter varies between -14 dB at 62 GHz when the bias voltage is 1.52 volts to a minimum of -21.74 dB at 57 GHz when the bias voltage is 1.7 volts. This indicates that the input matching network remains well matched as the bias voltage increases. The S12 parameter increases slightly from -54 dB to -50.35 dB at 60 GHz when the bias voltage changes from 1.52 volts to 1.7 volts. However, the input and output ports of the power amplifier still remain well isolated. The S22 achieves a minimum of -39.71 dB at 52 GHz. This is because of the load-pull matching technique being used at the output stage of the power amplifier. The small signal gain S21 increases from 16.56 dB to 20.66 dB because of the bias voltage increase from 1.52 volts to 1.7 volts. The peak power added efficiency, or PAE, of the linear power amplifier is 11.8% and 11% at the input power 1 dB compression point, compared to the non-linear power amplifier with a peak PAE of 12.6% and 3.63% at its input power 1 dB compression point, as shown in this figure. The reduced PAE of the linear power amplifier is expected because of the increased DC input power due to the dynamic bias mechanism. The third order intermodulation distortion component is shown in this figure. A 100 MHz tone spacing was used in the two-tone test to analyze this component. The use of the APD Linearisation technique results in a reduction of the third order intermodulation distortion component. Optimum reduction is achieved for output power between -7 and 3 dBm, with a maximum third order intermodulation distortion improvement of 10 dB being achieved. The complete IC consists of the nonlinear power amplifier in a black rectangle and the linear power amplifier and APD with their subsystems in the patterned rectangle. The entire IC occupies an area of 2 mm by 1.8 mm. The IC was first baked onto a supporting PCB, and gold wire bonds were used to connect the PCB pads to the bond pads on the IC. The supporting PCB was then placed onto a larger PCB as shown in the figure on the right. 3 ICs were mounted onto 3 PCBs and on-wafer probes were used to conduct the measurements. Because of layout restrictions, there is only one bond pad to provide the bias voltage for both the non-linear and linear power amplifiers. The bond pad restrictions were laid out by the RF probe interfacing and wire bonding requirements. It was recommended that the RF signal and DC bond pads be separated for the following reasons. The RF input and output bond pads should be located on the left and right side of the chip area respectively. Sufficient clearance between the DC wire bonds and RF pads should be provided. The minimum clearance distance set out by the infinity probes is 200 micrometer. This is to prevent the RF probes and wire bonds coming into contact. Any additional DC bond pads would interfere with the RF probes. Wire bonding was done on the DC bond pads. The wire bonding process required that all the DC bond pads be located in one line, either on top or bottom of the die area. Otherwise, the wire bonds might touch, and connecting it to the PCB contact would have been difficult. The DC bond pads took the maximum available space, and no additional space was available in a single line format for additional DC bond pads. Even if additional bond pads were available, long interconnects would still have been required. Because of the complexity of the entire system, each of the subsystems had to be tested separately to identify where the exact problem could be located. However, owing to the space restrictions of the multi-project wafer run, this was not possible. The problems mentioned above limited the measurement results. This slide shows how this research work compares with similar research as shown previously. This work uses a true power amplifier adaptive predistortion linearisation technique that can be configured to optimally reduce the third order intermodulation distortion component found in power amplifiers. The theoretical and mathematical analysis and results as discussed in this presentation have shown that APD is able to reduce the distortion components and improve the linearity of the power amplifier. Previous works have shown that APD can be used for linearity enhancement. However, these were based on different technologies but still focusing on linearity improvement using predistortion. Although the hypothesis could not be completely evaluated practically, the design methodology and simulations provide sufficient evidence, thus validating the hypothesis. The research questions were also answered, namely, a low complexity, high performance APD circuit can be realized to reduce the distortion of power amplifiers at 60 GHz using a voltage signal based on the output power of the power amplifier to increase the gain of the VGA, thereby realizing the predistortion function. With the use of APD, an optimum third-order intermodulation distortion reduction of 10 dB is achieved. The linear power amplifier has an improved linear output power of 2.5 dBm compared to the non-linear power amplifier. In the circuit design, some of the subsystems can be placed off-chip, especially the digital circuitry. Although this would not be a complete on-chip solution, it would provide additional space for the analog circuitry. Also, in future, with the availability of DC probes, on-wafer DC biasing can be done, eliminating the need for the supporting PCB and wire bonding. The use of other simulation environments, such as Agilent ADS with foundry support, can be investigated in future. These simulation environments can be used to verify the simulation and layout results from Cadence. Characterization of the active and passive devices for the IBM BiCMOS 8HP process using measurement equipment can also be investigated. This will provide invaluable information such as parasitic effects on the performance of these devices. Investigations into improving the efficiency of Class AB power amplifiers can also be investigated, such as using other dynamic biasing methods like switched dynamic biasing. The linearity improvement through the use of the APD in this research work focused on the amplitude aspect of the third-order intermodulation distortion component and not on the phase of this distortion component. Future work can be done on investigating and incorporating both amplitude and phase linearity improvement for power amplifiers at 60 GHz and above. The references used in this presentation are listed on this slide. As one can see, linearization of power amplifiers at millimeter wave frequencies is currently an active area of research. I would like to acknowledge the National Research Foundation for partially sponsoring this work, as well as Denal Dynamics for the use of their facilities and support. If you have any feedback or questions, you can contact me using the information on this slide. I thank you for your attention.